Section 1.6, More on Linear Systems and Invertible Matrices. A system of linear equations has 0, 1, or infinitely many solutions. There are no other possibilities. Let's prove this. If ax equals b is a system of linear equations, exactly one of the following is true. Either the system has no solutions, the system has exactly one solution, or the system has more than one solution. So if we can prove that in the last case where it has more than one solution, it actually has infinitely many, then we'll have proven our theorem. So let's assume that it has more than one solution. Let's look at that last case. Then we can let x0 or x0 be x1 minus x2, where x1 and x2 are any two distinct solutions. Because we have more than one, there must be, 1 and 2 at least. Because x1 and x2 are distinct, the matrix x0 is not 0. Because if these guys are distinct, then that means that there's no way we can subtract them and get 0. They'd have to be equal to each other in order to get 0. Moreover, if we take a look at a times x0, that's a times x1 minus x2, which is, we can distribute that matrix like that, and we know that that's going to be b minus b, because x1 and x2 are both solutions. So that means that a times x1 minus a times x2 is 0. If we now let k be any scalar, then a times x1 plus kx0 is equal to, well, again, distribute that a, and then we can take out the k, basically kind of just reorder this because it's a scalar, so it can come out. Notice ax1, remember x1 is a solution, so that's just b. ax0, well, that's 0. We already calculated that. So that means that ax1 plus kx0 is b plus 0, which is b. So that means that x1 plus kx0 is a solution, because we just plugged it in for x and we got b. So we just found a third solution. However, x0 is non-zero. There are infinitely many choices for k. So we just proved and we have infinitely many solutions. We just figured out that this will be a solution for an infinitely many different number of values of k. If A is an invertible n by n matrix, then for each n by 1 matrix B, the system of equations Ax equals B has exactly one solution, namely x equals A inverse B. Let's prove this. Since A times A inverse B equals B, it follows that x equals A inverse B is a solution of Ax equals B. It's what we just plugged into x and we got B out of it. So A inverse B must be a solution. To show this is the only solution, we will assume that x0 is an arbitrary solution, and then show that that x0 must be the solution A inverse B. Let's let x0 be any solution. Then A times x0 must be equal to B if x0 is a solution. But we could just multiply both sides by A inverse. And notice that just proved that x0 is A inverse B. So there is only one solution. As an example, how about we solve this system of linear equations? So we'll write A as the coefficient matrix. So A can be 1, 2, 3, 2, 5, 3, and 1, 0, 8. We'll write X as our solution matrix, or n by 1 matrix, or 3 by 1 in this case, x1, x2, x3. And we'll write our b as what this thing equals. It's 5, 3, 17. We actually computed A inverse in the previous section. That was example 4. So example from section 1.5, I'll call that 1.5.4, implies that A inverse is equal to negative 40, 16, 9, 13, -5, -3, 5, -2, and -1. So that means that x is equal to A inverse B. So it must be equal to this A inverse that we just wrote, -40, 16, 9, 13, -5, -3, 5, -2, -1, times B, which is 5, 3, 17. And if we do the matrix multiplication, we should get 1 minus 1, 2. Okay, so that means that the solution is x1 equals 1, x2 equals -1, and x3 equals 2. Let's try solving some more systems. Well, what we can do over here is notice that both of these systems have the same coefficient matrix. So we can solve both of them actually at the exact same time. Let's write out that coefficient matrix. That's 1, 2, 3, 2, 5, 3, 1, 0, 8. And it equals 4, 5, 9 in this case, and 1, 6 minus 6 in this case. So I'll adjoin those two columns, 4, 5, 9, and 1, 6 minus 6. Just put little separators. And we'll make that one big happy matrix. What I'll try to do now is put this thing into reduced to echelon form. So I want to get zeros over here. So I'll subtract 2 of the top row from the middle row, and I'll subtract 1 of them from the bottom row, aka add -1 times it. So I'll keep the top row the same, 1, 2, 3, 4, 1. And my second row, when I subtract 2 of the first row, will become 0, 1, -3, -3, 4. And my last row, when I subtract the top row, will become 0, -2, 5, 5, -7. Now I'll leave these little separators. And let's keep going, making good progress. Now the next thing I want to do is, oh, I have a 1 there, that's great. So let's get a 0 underneath over there. So I'll subtract, or in this case actually I'll add 2 of my second row to my third row so that I can eliminate that -2. So I'll get 1, 2, 3, 4, 1, 0, 1, -3, -3, 4, 0, 0, -1, -1, 1. Okay, good. All I need to do now is change this into a positive, and then I have row echelon form, which would be handy. So how about we do that? We'll rewrite the top. 1, 2, 3, 4, 1. Then we have 0, 1, -3, -3, 4, 0, 0, 1, 1, -1 after we multiply by -1 on the bottom. Okay, good. So now I've got my 3 1s that I wanted. I've got zeros underneath them. Perfect. To get to reduced row echelon form, I just need to introduce some zeros on top, over here and over here. How about we do these first, the -3 and 3. So what I'll do is I'll take my third row and I'll add 3 of them to this one, this whole entire second row, and I'll subtract 3 of them from the first row. So on the first row, I'll get 1, 2, 0, 1, 4. My second row becomes 0, 1, 0, 0, 1. And my third row stays 0, 0, 1, 1, -1. Okay, we just have 1 0 left to deal with. So I'll just subtract 2 of my second row from my first. I'll get 1, 0, 0, 1, 2, 0, 1, 0, 0, 1, and 0, 0, 1, 1, minus 1. Perfect. So we just solve both at the same time. For A, we'll just read up these solutions. So that gives us x1 equals 1, x2 equals 0, and x3 equals 1. For B, we get these solutions. x1 equals 2, x2 equals 1, and x3 equals minus 1. Let A be a square matrix. If B is a square matrix satisfying BA equals the identity, then B must be A inverse. If B is a square matrix satisfying AB equals the identity, then B must still be A inverse. Let's prove this. First, assume that BA is the identity. If we can show that A is invertible, then we can complete the proof by multiplying BA as the identity on both sides by A inverse, because notice that'll cancel out A, right? And then we'll just get B as A inverse, because B times the identity is B, I times A inverse is A inverse. To show that A is invertible, it suffices to show that the system AX equals 0 has only the trivial solution. So let's let x naught be any solution of the system. If we multiply both sides of AX naught on the left by B, then we'll get BAX naught equals B times the 0 matrix. But we know that BA is the identity. So it's the same as saying that the identity times x naught is the 0 matrix, which is the same as saying x naught is a 0 matrix. So that's a trivial solution. We just determined that the only solution is the trivial solution, so therefore A is invertible. Let's prove the second part of the theorem now. Assume that AB is the identity. By part A is equal to B inverse. By multiplying A equals B inverse on both sides, we obtain B times A equals B inverse, which means BA is the identity, and that means that B is A inverse by part A. So this gives us some more equivalency statements to add to our equivalent statements theorem. If A is an n by n matrix, then all of these are equivalent now. A is invertible, is equivalent to AX equals 0 having only the trivial solution, which is equivalent to the reduced row echelon form of A is the identity, which is equivalent to A as being expressible as a product of elementary matrices, which is equivalent to AX equals B being consistent for every n by 1 matrix B, which is equivalent to AX equals B having exactly one solution for every n by 1 matrix B. So if one of these are true, they're all true. If one's false, they're all false. Let's let A and B be square matrices of the same size. If AB is invertible, then A and B must also be invertible. So if we have the product invertible, then that means that each of the matrices that make up the product is invertible. Let's prove that. We will show first that B is invertible by showing that the homogeneous system, Bx equals 0, has only the trivial solution. If we assume that x naught is any solution of the system, then AB times x naught, which by associativity is the same as A times Bx naught. Remember, Bx naught is 0, so that means that A times 0 is 0. So we have A Bx naught is 0. So that means that x naught must be 0 by this theorem right over here, because we have that AB is invertible. That was our assumption. So AB is invertible. ABx equals 0 has the only the trivial solution. Okay, so that means x naught is 0, and the invertibility of B implies the invertibility of B inverse, which in turn implies that AB times B inverse, which is A times B inverse, is A. So that must be invertible since this is invertible, this is invertible. It's a product of invertible matrices. What conditions must B1, B2, and B3 satisfy in order for the system of equations given to be consistent? Well, how about we write out the matrix for the system. Coefficients are 1, 1, 2, B1, and 1, 0, 1, B2, 2, 1, 3, B3. So how about we see what it would take to put this into a reduced row echelon form. Well, let's see. We'll write out 1, 1, 2, B1, and I want to get zeros over here. So I'll subtract my first row from my second. I'll get 0, minus 1, minus 1, B2 minus B1, and I'll get 0, minus 1, minus 1, B3 minus 2 times B1, because I'll subtract 2 of the first row from my last one to cancel out that 2. Okay, so then I'll keep going, and I'll get, it's like my top is still good. I would like to get a leading 1 over here, so I'll multiply that by negative 1. So I'll get 1, 1, 2, B1, and I'll get 0, 1, 1. I'll just change the order, B1 minus B2. That's multiplying by a negative. And my last row I'll leave the same, 0, minus 1, minus 1, B3, minus 2, B1. Okay, I'm making progress. Wait, notice this is 0, 1, 1, this is 0, minus 1, minus 1. I'm going to cancel out the third row entirely. I'm just going to get zeros over there if I add the second row to it. So I'll get 1, 1, 2, B1. I'll get 0, 1, 1, B1 minus B2. My third row will just be 0, 0, 0, B3 minus B2 minus B1. Remember, I'm adding all of this row to this row. So I had to add B1 minus B2 to B3 minus 2B1. The minus 2B1 plus 1B1 gives me minus B1, and then I just kept my minus B2. So this means that we have this thing equals 0. Okay, so I could write B3 minus B2 minus B1 has to be 0. That's the same thing as solving for B3 and saying that B3 has to be B1 plus B2. So that means that we only have AX equals B consistent whenever B is equal to whatever B1 is, whatever we want for B2, but B3 has to be B1 plus B2. What conditions must B1, B2, and B3 satisfy in order for the system of equations given here to be consistent? Let's see, once again, how about we write out our coefficient matrix. So 1, 2, 3, and we'll write B1, 2, 5, 3, B2, 1, 0, 8, B3, and we'll attempt to put this in reduced row echelon form. Okay, so how about I try to get, again, zeros over there. So I'll get 1, 2, 3. I'll keep my first row the same. B1. My second row becomes 1 minus 3. B2 minus 2B1. And my third row becomes 0 minus 2, 5, B3 minus B1. Okay, I already have my leading one over there. Let's just get a 0 underneath. So I'll keep going, and I'll get 1, 2, 3, B1, 0, 1, minus 3, B2 minus 2B1. As for my third row, though, I'll have to add 2 of these guys. So I'll get 0, 0, minus 1. I'll keep B3 minus B1, but I'll add 2 of this. So that's B2 minus 2B1. To be kind of careful with the constants when we don't know what they are, to keep track of them. Okay, so let's just make that positive. We'll keep the top, 1, 2, 3, B1, make this 0, 1, minus 3, as before, B2 minus 2B1. My bottom row becomes 0, 0, 1, and I'll multiply this by negative, and I'll just simplify it a little bit, and I'll get 5B1 minus 2B2 minus B3 by combining like terms. Okay, let's keep going. I would like to get zeros over here now. So adding 3 of this to here, and I'll add negative 3 to the top row. So my top row becomes 1, 2, 0, B1 minus 3 times the bottom row constant was 5B1 minus 2B2 minus B3. And my middle row becomes 0, 1, 0. That constant was B2 minus 2B1. And now I'm adding 3 times the bottom row, 5B1 minus 2B2 minus B3. And then my last row is still 0, 0, 1, 5B1 minus 2B2 minus B3. Okay, let's keep going. All I gotta do is get rid of that 2 now, it looks like. So my top row, I'll subtract 2 of the second row from it. So I'll get 1, 0, 0. We'll simplify this. Get negative 14B1 plus 6B2 plus 3B3. And we'll subtract off 2 of this row, and I'll simplify that as 13B1 minus 5B2 minus 3B3. And my second row I'll leave, but I'll just simplify that constant. So it's, again, 13B1 minus 5B2 minus 3B3 once it's simplified. And my last row stays 0, 0, 1, 5B1 minus 2B2 minus B3. How about we just simplify that top constant, because it looks a little bit messy. So this thing is exactly the same as 1, 0, 0, negative 40 B1 plus 16 B2 plus 9 B3. We'll just reproduce our other rows. So 13 B1 minus 5 B2 minus 3 B3 and 0, 0, 1, 5 B1 minus 2 B2 minus B3. Okay, so this means that x1 has to equal negative 40 b1 plus 16 b2 plus 9 b3. x2 has to equal 13 b1 minus 5 b2 minus 3 b3. And x3 has to equal 5b1 minus 2b2 minus b3 in order for the system to be consistent.